Hey, what's up, guys? This is Mr. Lowry. We are in chapter 11 of our Big Ideas math book now. We skipped some stuff in chapter 10, but we kind of hit the relevant stuff. We talked about the corresponding angles theorem, alternate interior angles, alternate exterior angles, and consecutive interior. Those are kind of really big ideas that are going to be important and that you're going to see again in 10th grade. But we kind of need to move to this next chapter because this is going to be important stuff as well. And this chapter 11, is pretty short. It's only 4 sections. So we're probably going to be able to cover it in just a few days. And it's actually not very hard. It's kind of weird that we're moving from proofs, and then it looks like we're kind of going back to like the coordinate plane, which we are. And then we're going to go back to proofs in chapter 12. The reason why this is kind of in the middle is because we need some of these ideas about transformations in order to justify some of the other proofs that we're going to be doing. Okay? For example, if you recall, we talked about this idea at the beginning of one of our lessons when we proved the corresponding angles theorem. And it's this idea that a rigid motion is a transformation that preserves length and angle measure. So if you remember from that video, I took like a triangle shape and I reflected it and I rotated it and I moved it around, and that was kind of a way to introduce the corresponding angles theorem. So we're actually going to go through now and talk about transformations in this chapter, and then in chapter 12 we got to go back and talk about a few more theorems that we want to prove. Okay. So, the first little bit here, you're going to have an assignment that you're going to be doing. Looks like this: translations and reflections. We're actually going to cover 11.1 and 11.2 in this video, and it sounds like a lot, but it's going to go pretty quick. And you're going to have a couple days to work on this. So, the first section here is just definitions. Okay, so we're going to go through some of those definitions, and these are in your book. Most of them, and if they're not, then I'll help you answer them as well. So we want transformation, image, pre-image, translation. We're going to go through some of these key terms together. So make sure you have this out. Get this out. If you don't have it out already, pause the video, print it out or whatever, or you can write it down on a separate sheet of paper, whatever it takes, and then you can come back to the video and get started, because we're going to hit these as we go. Okay, the first definition that we want to talk about is transformation. This guy right here. Okay, and this is on page 544. So transformation is a function that moves or changes a figure in some way to produce a new figure called an image. Okay, so if we wanted to take like a triangle, for example, and we want to like slide it around, that's going to be like, you can think of it as a function. You have an input, this guy, and you have an output, this guy. Right? So we move or change the image or the figure in some way to get a new figure. Okay? The original figure or the input we call the pre-image. In this case, it's blue. And then same thing down here. We have another example, right? There's blue. And then the final, the output, is called the image. Okay? So transformation is a function or some kind of, operation kind of thing that we perform on a figure that gives us a new figure or a different figure. Okay? The new figure, again, the output's called the image. And then the original figure is called the pre-image. Okay? The points on the pre-image are inputs for the transformation, and the points on the image are the outputs. Right? That's kind of the idea. So that's an important concept. So that gives you kind of 3 right off the bat, right? We have transformation, we have image, and we have pre-image. And we hit all of those in just a couple sentences. So put those in your own words, but image is the after and pre-image is the before. Okay, now transformations is just a generic or a general term. Okay, there's specific types of these moves or changes that we're going to do. The 3 that we're going to look at specifically are translation, reflection, and rotation, which I referred to again in the video from last week where we talked about corresponding angles theorem. So in this section, we're going to focus specifically on translations and rotations. And then in the next lesson, we're going to do, translations and reflections today. The next time we come back, we're going to do rotations, right? So there's 3 of them, 3 big ones. So now we're getting into the specifics. Again, this is the generic umbrella term for lots of different kinds of things. And this translation is a specific of this general term. Okay? So a translation is a type of transformation. Okay? Specifically, this kind of transformation is basically like a slide. We're like sliding something around or shifting something around. Okay? So a translation is a transformation that moves every point of the figure the same distance and in the same direction. Okay? So for this, in this case, we have a segment, and this point goes up and to the right, and this one goes up and to the right, and they go the same distance. And the end result looks like the original, it just looks like it moved, basically. So this again is called the image, and the original is called the pre-image. Okay? So what this is saying right here is from some point P to its image is the same distance as the point Q to its image. So what this means, this little symbol right here looks like an apostrophe. Let me zoom in. This little symbol we say P prime. Okay? So if we have an original point P, when we transform it, the image we call P prime, which is the image of P. Okay? When we transform Q, we get Q, there we go. We get Q prime, or the image of Q. Sorry. So what this is saying is the distance between a point and its image is going to be the same. Also, the lines that connect those points are going to be parallel to each other. So that's kind of neat, kind of interesting. Okay. So we talked about translation, right? Translation is the next definition in your worksheet. And it's a transformation where every point of the figure moves the same distance in the same direction. Okay, the next term is called rigid motion. So we're gonna jump to the next page, and then we're gonna come back and we'll talk about transformations a little bit more. Okay. So a rigid motion is a transformation that preserves length and angle measure. Okay, so if I do a transformation where I move something around, like a triangle, for example, I'm not changing the angles of the triangle. I'm not changing the lengths of the sides of the triangle. So that's kind of what that means. Another word for this is an isometry. Okay, you'll also see this word maps. Okay, what that means is when they say maps, that basically means like the input goes to the output, or matches. Like when we do functions and we have an input that matches to an output. Another way to say this is this input maps to this output. So like A maps to A prime, and B maps to B prime, and C maps to C prime. And triangle ABC maps to triangle A prime, B prime, C prime. So that word maps just means like matches to it. The function, it turns one into the other. Okay, so a rigid motion maps lines to lines, rays to rays, and segments to segments. It also maps polygons to polygons, so like triangles to triangles, like you'll see here. So shapes to similar shapes. Okay. So a rigid motion is just, it's a move where you don't change the angle measurements or the segments. Okay. Now there's actually multiple different categories of rigid motion. So every rigid motion is a transformation, okay? And there are several different rigid motion categories. So number 7 here says list the categories of rigid motions. So you got a translation is a rigid motion. A reflection is a rigid motion. And sorry, my allergies are killing me, so if I'm sniffly, I apologize. Rotation is also a rigid motion. Okay. Also, any like combination of these will also be a rigid motion. Okay. So, if you'll notice, it says translation postulate. A translation is a rigid motion. Okay. A composition of 2 or more rigid motions is also a rigid motion. Composition is like when you combine more than one. Then later, when we talk about reflections, there's this postulate, reflection postulate. A reflection is a rigid motion. And then when we talk about rotations, a rotation is also a rigid motion. Okay, so those are some categories of rigid motions. You got translations, reflections, rotations. All the ones that we're going to talk about this year are rigid motions, meaning when you do that transformation, they don't change angles or segment lengths or things like that. Okay, and I'll kind of demonstrate that as we get into the problems themselves. Okay, so we got transformation, image, pre-image, translation, rigid motion. We talked about the three categories. Let's talk about reflection real quick. Okay, so reflection is in 11.2, and a reflection is a transformation that uses a line, like a mirror, to reflect a figure, and the mirror is called a line of reflection. So if this is the line of reflection here, and you have a point P, this is kind of like a mirror. So you have a point looking in the mirror, and it sees this image in the mirror, right? Notice that the point is the same distance from the mirror as the image is from the mirror. So if you're looking at yourself in the mirror and you're 5 feet away, your image should also look 5 feet away. So these distances match each other. Also, the way we measure distances from a point to a line is always perpendicular. So we're going to measure, that's why there's this right angle, we measure perpendicularly. So one of the important things to know is, this says, if P is not on M, then M is the perpendicular bisector of the line segment P prime. Let's think about what that means for a second. If you're not standing right at the mirror, you're farther away, then that means, again, that this distance from P to the line is the same as the line to P prime. So if this line, P to P prime, is a segment, notice it's getting bisected by the mirror. The mirror cuts the segment from a point to its image in half, in two equal halves, or two congruent halves. That's what that means right there. Okay? If P is on M, then P equals P prime. What that means is, like, imagine that you're standing with your nose on the mirror, right? If you're standing with your nose on the mirror, then in your reflection, your nose is also on the mirror, and it's like almost like your reflection is touching you. They're in the same spot. So that's kind of what that means. But this idea of the distance from the point to the mirror is the same as the mirror to the image is going to be an important idea for us. Okay, let's get into some problems, okay? All right, so what we want to do here, this is translation. It says, graph the image of the figure using the transformation given. So this is the figure, right? It's also called the pre-image, right, the original. And we want to graph the image, right? So this says translation, 6 units right and 1 unit down. And what we read about translations is that, what we read about translations is that every point moves the same distance in the same direction. So we can start with point like B, for example, and we know this goes 6 to the right and 1 down. So we're just going to take B, and we're going to go 1, 2, 3, 4, 5, 6, so 6 to the right and 1 down. And when we label this, we're going to label it B with a little apostrophe. And again, that's B prime. So if we wanted to, we can draw an arrow. We'll do that in a minute to show that transformation, but let's just keep going. Let's take point C. Okay, so C, we also have to go the same direction and the same distance. So 6 units to the right, 1, 2, 3, 4, 5, 6, and 1 unit down. And we're going to call this guy C prime, or the image of C. Okay, D, we're going to go 1, 2, 3, 4, 5, 6, and then down 1. This is D prime. And then E, we're going to go 1, 2, 3, 4, 5, 6, and down 1. And this is going to be E prime. Okay, so I'm going to grab my ruler, and I'm going to connect the dots to make this image. It's going to look a lot like the original, just in a different location. Okay, so basically this whole shape just went to the right 6 and down 1. Every point on it did that. So we call that a rigid motion. Now what we can do is we can make kind of arrows that show that move, right? We can show that they're all going the same distance in the same direction. Okay, so you can see these lines, they're all parallel. They're also all the same distance because they all, like if we did the Pythagorean theorem, and we went 1 squared plus 6 squared and took the square root, we would get the same like diagonal distance for all 4 of these, excuse me. Now the reason why we call this a rigid motion, now this is a translation, but translation is a subset, or it's a member of the rigid motions, and rigid motion is a member of the transformations. So there's kind of these different groups or whatever. And if we were to, like make a Venn diagram to kind of show that, since we did this with polygons, we could say, okay, here's all the transformations that exist. Okay. Now within transformations, you have a subgroup called rigid motions. And rigid motions preserve length and angle measure. So for example, from B to C is the same as B to C prime. Like I didn't change the length of this segment here. It's still the same length. And I didn't change the length of this segment. And I didn't change the length of this segment, right? This B to E is the same distance, or the same length as B to E prime, E prime. And this is the same as this one, right? It looks the same. Also, this, whatever angle this creates, DEB, is still the same, DEB. This angle measure hasn't changed. This angle measure CBE and C prime, B prime, E prime, that's the same angle measure. So that's what a rigid motion does. Now there's other kinds of transformations that we're not going to talk about this year, like what we call a dilation, where you like make the shape bigger or smaller, and that will change lengths and stuff like that. So there's other types of transformations. We'll focus on the rigid motions, which are translation, reflection, rotation. Okay, those are the 3 rigid motions. And then any combination of these will also be a rigid motion. Okay, so let's make sure we got everything. We wanted to graph the image of the figure. Okay, check. We use our rule. Check. Okay, looks like we're good to go there. Okay, I'm going to let you guys do number 9, and it should be pretty easy for you. Let's do the same kind of thing that you did here. All right, let's look at number 10. Okay, now this right here is what's called a translation rule. And the difference between this problem and the problems we did in 8 and 9 is that in this problem, instead of using words, they're going to use symbols. And so what this means is for any point x, y, it doesn't matter which point, this point can refer to any of these 4 points. But what you're going to do is add 3 to the x's and subtract 1 from the y value. Okay, so let's see what that means. Let's take one of these points. For example, let's take point D. Right? And D right now is at 2, 1, 2, 1, 2, 3, 4. D is at 2, 4. And so what we want to do to get D prime is we want to take the x value and add 3 to it. So now it's going to be sitting at 5. And then to get the y value, we take whatever the original was and we subtract 1. Oh, sorry. Subtract 4 minus 1 would be 3. Okay? So we got 1, 2, 3, 1. So this is D prime. Okay, so what did that do? Well, we went to the right 3, which makes sense because we're adding 3 to the x value, and we went down 1. So if I'm adding 3 to x, positive in the x direction is this way. All right, so that's to the right. Negative in the y direction would be that way. So this is just right 3, down 1. Okay. Now, that's the same rule for all of them, so we're going to move all of them right 3 and down 1. And you could do it this way if you wanted to, with like points, and you could write them out and do the arithmetic. But you actually just can look at it and know, hey, that means right and that means down. So let's just keep going. So right 3, 1, 2, 3, down 1. Okay, that's E prime. Start with B, 1, 2, 3, down 1. That's B prime. Okay, C, we're going to go right 3, 1, 2, 3, and down 1. And that's C prime. Let's connect the dots, and we'll see that this is indeed a rigid motion. There's my C prime. Sometimes these shapes overlap, and that can get a little bit tricky. But if you got your points in the right spot, then usually you're pretty good. and there's C prime to D prime. Okay, so the dark black one is again called the pre-image, and this guy is called the image. We moved every single point, right, 3 and down 1, which gave us this image. And notice that all the segment lengths are preserved, so this length and this length are the same, and this are the same, and this are the same. All the angles are going to be the same, so CDE is the same as C prime, D prime, E prime. Right now the angles have changed. It's basically the same figure, it's just in a different spot. Okay, that's a rigid motion. So remember, a translation is a rigid motion, and a rigid motion is a group of translations, and they're in the translation family. Okay, so let's look at what this one means. Okay, x goes to x. So what happened to the x? Nothing. Okay, that means it doesn't move left to right at all. What about y plus 6? Well, that means up 6, right? Take all the y coordinates and add 6 to it. That's going to be up 6. Okay, so every point here is going to move up 6, but it's not going to go left and right. I'll let you guys finish that one. Okay, the next problem set, also transformations. Okay. So in this one, we want to write a rule to describe each transformation. What that means is we want to write something that looks like this. That's what we're after. We're going to say, okay, this is the rule. Take whatever point you're at and then do this to it. Okay? The first thing, and kind of maybe sometimes the hardest thing, or the thing you got to pay attention to, is you got to figure out which is the image and which is the pre-image. And you're going to be able to tell that by the apostrophe symbols. So this is the original, the black one, because it doesn't have those apostrophes. So this is the pre-image. The image has those little apostrophes, which we call prime again. So we got J, there's J prime, I prime, K, and K prime. So what we're doing here is we're going this way. We're going from J to J prime in this direction, right? So I'm going to draw arrows. You don't have to draw arrows every time, but just so we can kind of see some direction here. So that guy's just sliding down. We just got to figure out how much. So we're going to start with the left, right. So we're going to go right 2 and then down 3. That's what J does. But that's also what I does. Right 2, down 3. And then, so sorry, right 2, down 3. And then from K, right 2, down 3 to K prime. So we just want to be generic, right? We don't want to take a specific point like J or K or I. We want to take a generic point, any point x, y. What happens to this point? This is going to be basically the input or the pre-image. And what happens to that, to do the transformation that we want, is we got to go right 2, so x plus 2, and then we want to go down 3, so y minus 3. Okay, that's your translation rule. Now, because there's other types of transformations, we kind of want to be specific. So we're going to put translation, just so we can say, hey, this is a translation, by the way. It's not a rotation or a reflection. And this is how you do it. Each point, x, y, has to go to x plus 2, y minus 3. Or whenever you put an x in, add 2 to it. Whenever you put a y in, minus 3. And you get from the original pre-image to the image. Okay, so you're going to do that for these guys, same kind of idea. Now again, be careful that you identify the image and the pre-image before you start, otherwise you could be going in the wrong direction. So yours might be black and white, or yeah, just black and white. Mine has some blue on it. So this one here, if you're thinking, oh, it's going down and right again, it's actually not. This is the original, this is the pre-image, right? Excuse me, this is the original, which is called the pre-image, and this is the image. So I'm actually going this way. I'm going left and up. Okay, so left would be minus 2, up would be plus 3. So that'll help you with that one. And then you guys can do 14 and 15 on your own. Okay, now we're going to do some reflections. Okay. What we know about reflections is that the distance from the image to, the distance from the pre-image to the mirror is the same as the mirror to the image. Okay, so that's what we're going to use to help us. In this case, this tells us it's a reflection, and it also tells us where to put the mirror. So the mirror, the line of reflection in this case, is going to be the x-axis. So I'm going to kind of darken that a little bit so we can remember. Okay, so that is our mirror. So imagine this little guy, this little quadrilateral, is looking at himself in the mirror. Okay, what we know is that the distance from this point W, let's say his nose or something, to the mirror has to be the same as the mirror to the image of his nose. So we just figure out how far away is W from the line, and we go that same distance again. So that's 1 unit. We're going to go 1 unit on this side, and that's going to be W prime. Okay. For V, we got V is 2 units away. So maybe that's his ear, like this is his head, and we're looking down on top of him or something. So V is 2 units away from the mirror, which means that the image of V has to be 2 units away from the mirror in like the reflection. Sorry, there's a little bit of glare on the paper here. Okay, let's look at U. U's the back of his head. Okay, so U, the back of his head. Now, obviously, we wouldn't be able to see this in the mirror, but if we could, U would be 1, 2, 3 away from the mirror, which means the image of U should be 1, 2, 3 away from the mirror as well. So this is U prime. Okay, and then X, I don't know, this could be his other ear, and maybe he's like, a mutant or something. But X is 3 units away from the mirror, and so X prime, or the image of X, will be 1, 2, 3 units away as well. Okay, so different transformation altogether. This is not a translation. We're not shifting. We're not sliding. We're flipping it. We're reflecting it. Okay, let's connect the dots here. Okay, now in a reflection, you actually change the orientation of the shape. Orientation, it means like which way it's facing, right? So if this was like the nose, that was facing this way. Now the other one is facing the opposite direction. So the orientation changes, or the position changes, or the way it's facing changes. But it's still a rigid motion, because notice that from W to X is the same distance of W prime to X prime. It's still the same length. You can see that. From V to W is the same distance as V prime to W prime. From U to X is the same distance as U prime to X prime, right? So all those segment lengths haven't changed. Those segment lengths have been preserved. Also, all the angles are still going to be the same. So like this angle, VWX, is still going to be the same as V prime W prime X prime. So this guy is still going to be the same as this guy. They're going to be congruent. Okay. So this is an important idea because we use this to talk about congruent angles and congruent segments and stuff, which we use in proofs quite a bit. So knowing the idea of rigid motion is important because you use rigid motion and the idea that it preserves segment lengths and angle measurements to be able to prove stuff. Okay, so that's my reflection. That's all we really needed to do. That's how it works. Now you're going to do one across the y-axis, so I'll get you started on that, but you're going to finish this one up. Okay, so this time the y-axis is this way. So if we want to reflect this way, now this is the mirror. So P is 1, 2, 3 away. P prime should be 1, 2, 3 away. Okay, there's P prime for you. I'll let you finish. If you think about taking this shape, though, and flipping it over to this side, that's what it's going to look like. So, or if you were like, I'm going to take this, I'm going to fold it over, that's kind of what it's going to look like. You can't really see that, but I can kind of see through the paper there. Anyway, so that's kind of the way to think about it. Okay, now you don't have to reflect over an axis, right? You can reflect over any line. This is reflecting over the X, this is reflecting over the Y. You don't have to reflect over any specific line. You can reflect over any line at all. So let's do one where it's not reflecting over an axis. So this is reflecting across the line y equals 2. We have to remember that y equals 2 is a horizontal line, right? It crosses the y-axis down at -2. So it crosses the y-axis, right? Crosses the y-axis at -2. So that is my line of reflection right there. I'm using this as my mirror. So this is a little bit tricky because this image, this doesn't happen in real life, but imagine that like you're halfway through the mirror, right? So that's kind of weird, but we can still do it. Let's start with L, K, and N, and then we'll come back to M. So here's our mirror. L is 1 away from the mirror. That means L prime needs to be 1 away from the mirror. All right, K is 1, 2, 3 away from the mirror. K prime needs to be 1, 2, 3 away from the mirror. On the other side. N is 1 away from the mirror, so N needs to be 1 away. So N prime is over here, where M is, and then M is 1 away from the mirror, and so M prime is 1 in this direction. So it's almost like M and N kind of switch places to become N prime and M prime. And so this one is reflecting over this side and this is reflecting over here. So let's connect up the dots here. Okay, got L prime to K prime, and then we got K prime to N prime. Okay, so that's what it looks like. It's kind of cool because they're overlapping now, and you can make some kind of cool images with this. But that's how you do a reflection across a different line. Same kind of idea. Okay, now number 19, we're reflecting over x equals 3. So we have to remember that this is a vertical line, right? It crosses the x-axis at 3. So that's x equals 3 right there. I'm going to let you guys finish this reflection. But one thing I will say is that since G is on the mirror, G prime is in the same spot. So G and G prime are in the same spot. This is also G prime. We talked about that a minute ago. Okay, so let's go up here. And now we're going to talk about writing rules for these transformations. Now these are reflection rules. So we're going to do something kind of similar. If you remember with the translations, we wrote these translation rules. What happens to x, y? What do we do with it? Okay, we're going to actually do that for some of these as well, which is not, it's kind of interesting. So first of all, we need to find our mirror, right? Okay, so we can find the line of symmetry, which is right there. It's the y-axis. Okay, so we know this is a reflection over the y-axis. Okay, let's actually list out the points though and see what happens, so we can see what we can write a rule basically. Okay, so let's write all the points out. We're gonna write V. We'll write them in alphabetical order. So that would be T, U, V, W. Okay, we're also going to write out T prime, U prime, V prime, and W prime, just so we can see like what is happening to each of these points. Okay, so T is right here. That is at 0, -4. And then T prime is also at 0, -4. Okay, U is at, oh sorry, that's 1, 2, 3, that's -3. Sorry. Okay, U prime is at 0, -2, and then, sorry, U is at 0, -2, but also U prime is at 0, -2. Okay, V is at -1, 0. V prime is at 1, 0. And W is at 1, 2, 3, -3, 0. And W prime is at 1, 2, 3. Oh, sorry. I got that wrong. It's -3, -3. Sorry about that. W prime is at 3, -3. Okay, let's start by looking at the y values. -3, -3. Okay, that's the same. -2, -2. Okay, that's the same. 0, 0. Okay, that's the same. -3, -3. Okay, that's the same. So the y-coordinate hasn't changed at all. Nothing's happened with the y-coordinate. Okay, let's look at the x. Okay, 0, 0, that doesn't really mean anything to us. 0, 0, okay. Negative 1 becomes a 1, and negative 3 becomes a 3. Okay, so what's happening is we're getting the opposite of the x value. Now here, if we take the opposite of 0, it's still 0. Opposite of 0, 0. But the opposite of negative 1 is positive 1. And the opposite of negative 3 is positive 3. So anything that's over here in negative land, when I reflect it, ends up over here in positive land. So to write this rule, I say, okay, I start with some point xy, which is always how your rules start. This just represents any generic point. And what you want to do to it is you want to take the opposite of whatever x was, but then keep the same y. Okay, so with the translations, we added numbers. We took x plus 3, x minus 2, y minus 2, y plus 1, right? That kind of stuff. In this case, we don't need to add anything. We're just switching the signs, basically. That's kind of the pattern that you see here. Okay, so this guy, if we draw the line of symmetry, this is a reflection over the x-axis. Okay, now you're going to see something kind of similar, but a little bit different, and I'll give you a hint. When we reflect over the x-axis, the x-coordinate doesn't change, right? Let's look at v for a second. V is 1, negative 1. But what's v prime? It's 1, 1. So the x-coordinate didn't change, but the y-coordinate did. See that? So that's a hint. You're going to write a rule that's kind of similar like this. You're going to xy does something. What does it change to? What's the rule? What do we do with the x's? What do we do with the y's? Okay, so it's going to be similar to this, but there's going to be a little bit more to it. Okay. We got a couple more here. In this case, we have a couple diagonal lines. So diagonal lines can be tricky, and I want to walk through that with you to help you figure out, what's the pattern here. Okay, so if I'm going to draw the line of symmetry on this guy, it's a diagonal line. Okay, just like that. And notice that the distances are the same, but the distances are going diagonally. What I mean by that is from J to the mirror is the same distance as the mirror to J prime, but we have to measure like across the grid, like diagonally, which is kind of weird. And that can be really tricky to do. So I'm going to show you how to do that. We also need to identify what this line is. So think slope-intercept form, y equals mx plus b. What's the y-intercept of this line? 0. What's the slope of this line? Up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. So this is y equals 1x plus 0, which is the same as y equals x. So this transformation right here is a reflection over the line y equals x. Okay? So what we're going to do is we're going to come up with a rule for this, and then we're going to be able to use that rule down here. A lot of the transformation, or a lot of the reflections are really easy to do, but these ones with diagonal lines can be tricky. So I'm going to show you a trick to do that. Okay? So let's list out the points in alphabetical order, H, I, J, K. And this is H prime, I prime, J prime, K prime. Okay, so H is here, and it's at 0, negative 3. Okay, where's H prime at? It's at negative 3, 0. Okay, where's I at? I is at 2, 0. Right there. Where's I prime? 0, 2. Interesting, interesting. Okay, where's J? 3, 0. Any prediction on where J prime might be? If you were thinking 0, 3, you would be correct. So hopefully you're starting to see a pattern here. Okay, and then K is at 4, -3. Where's K prime at? -3, 4. So what's happening here? The X and the Y are switching position. So if I take some point, XY, and I want to reflect it over this line, all I have to do is switch the coordinates. This is my transformation rule right here. Okay? That's actually going to help us quite a bit. So with that, let's jump down and look at 24, which is the opposite, and then we'll come back to 23 and 25. Okay? So a reflection over the line y equals x. First thing we need to know is, what does the line y equals x look like? It's a line, a diagonal line, with an intercept at 0 and a slope of 1. Okay, that's the line y equals x. That's our mirror. Now from here, you could kind of like try to, measure this and see how far it is away, like diagonally, and try to reproduce that over here. But that can get kind of tricky. It's easy to make mistakes when you do that. Some people are okay at it. You're like, well, I think A prime is going to go right here. I think B prime is going to go here. But like C, I don't know, it's kind of hard to get it in the right spot. So this is what I do. When I am trying to do a reflection over this line, I don't do it visually. I do it coordinates-wise. So let's take A, B, C and just figure out where they're going to go. A is at 0, 1. B is at, looks like 4, 3. Let's double check that. 1, 2, 3, 4, 1, 2, 3. Okay. And then C is at 3, 0. Okay, that means that all I have to do, if I want to reflect over this line, just using this rule, which is true for all reflections over this line, anytime you have a reflection over y equals x, this is the rule. You just switch them. So A prime is going to be 1, 0. And B prime is going to be 3, 4. And C prime is going to be 0, 3. Okay, so 1, 0. There's A prime. 3, 4. 1, 2, 3. 1, oops. 4, 3, 3, 4. Yeah, 1, 2, 3, 1, 2, 3, 4. Right, okay, sorry. B prime. Okay, and then C prime should be 0, 0, 3. Now, you may have been able to do that without that rule, but sometimes people have a hard time with that. And so being able to discover a rule or like find a pattern, figure out what's happening to your points, will kind of allow you to do some of these transformations without making mistakes. So that's what that should look like. Okay, almost there. Hang in there with me. So for 23, we got to do something similar. First thing we're going to do is find the axis or the line of reflection, or the mirror, which is also the line of symmetry. Okay, in this case it looks like this. That's my mirror. Now this line, we got to figure out what this line is. Well, this line, again, think slope-intercept form, still has an intercept of 0, but this guy has a slope of -1, down 1, right 1, down 1, right 1. So this is y equals -1 x plus 0. In other words, it's y equals -x. So this transformation that's happening is a reflection over y equals -x. Okay? Let's see if we can figure out a rule. So let's write the original. That's TUV. Oops. And let's see if we can see a pattern when we find T prime, U prime, V prime. So T is at -1, -1. U is at 2, 3. And V is at 1, 2, 3, -1. Okay, T prime is here at 1, 1. U prime is at here at -3, -2. And V prime is at 1, -3. Okay, so let's see what's happening. This one's kind of hard to see, but if you look at the other ones, 2, negative 2, 3, negative 3. 3, negative 3, negative 1, positive 1. So what's happening is the sign is changing. Not only they're switching positions, but we're also taking the opposite of what we started with. So this 2 in the x position becomes a negative 2 in the y position. This 3 in the y position becomes a negative 3 in the x position. This positive 3 in the x position becomes a negative 3 in the y position. And this negative 1 in the y position becomes a positive 1 in the x position. And that's the same thing here. It's just harder to see because these are the same numbers. So what's happening is that x, y is changing so that it's negative y, or the opposite of y, and then the opposite of x. It's switching signs, and they're also changing position. Okay, so that's the transformation rule for this guy. Okay, let's see if we can use that down here. Sorry, let me go back. I think I said it. We're going to do 23 and 25. 22, 24, and 25 all go together. So to do this one, a reflection over y equals x, you're just going to do the same thing you did here. Reverse them. Okay. Now down here on the last two, this is where we're reflecting over y equals negative x. And in that case, we're going to use this rule. Swap the positions and change the signs. Okay. So let's do that real quick. Okay, so that's y equals negative x, right? Has an intercept of 0 and it goes down 1, right 1. That's the line we're talking about. And any reflection over y equals x, we're going to have this rule. It's going to do this thing. We're going to take whatever point we start with, and what we're going to want to do is reverse the order and take the opposite of the sign that we had to begin with. Okay, so let's do u, v, w. Now u isn't going to be very fun because u is at 0, 0. So when you switch the order and change the signs, you're still going to have 0, 0 because the opposite of 0 is still 0. Okay, these are going to be a little bit more interesting. We got a negative 1, negative 1 and 5. Okay, so v prime would have to be a negative 5 because this positive 5 is going to switch to this position and become negative. And then this negative 1 in the x position is going to become a positive 1 and it's going to go in the y position. Sorry, my eraser marks are a little... There we go. Okay. All right, so for w, we got 1, 2, 3, 1, 2, 3, 4. So 3, 4 is w. W prime should be at negative 4, so the y, the 4 in the y position is going to become a negative 4 in the x position. The positive 3 in the x position is going to become a negative 3 in the y position. Okay, now let's just see if that checks out, if that looks like a reflection. Okay, u prime is at 0, 0. Okay, that's fine. It's the same spot as u. V prime is at negative 5, 1. So 1, 2, 3, 4, 5, 1. Okay, and then w prime is at negative 4, negative 3. So 1, 2, 3, 4, 1, 2, 3. And this is w prime, and this is v prime. Let's see if it looks like a reflection. Okay, looks pretty good. So the distance from the v prime, the image, to the mirror is the same distance as the mirror to the pre-image. And the distance from w prime to the mirror is the same as the mirror to w. And then, of course, u and u prime are in the same spot. Okay, so that's how you do that one. These ones are a little tricky, so don't try to freestyle this one. Don't try to just eyeball it because you're gonna get in the wrong spot. For the diagonal lines, I recommend that you actually use the transformation rules. So for number 25, draw the line in there, of course, and then use this rule. In other words, take every coordinate and just switch the order. Don't worry about the signs. Keep the signs exactly the same as they are. Just change the order of them, and that will give you your image. For reflection over y equals negative x, which is the line that goes diagonally, you're going to switch the order, right? But you're also going to take the opposite sign that you started with. And that's going to give you your image. Okay, so reflections are pretty easy to do for the most part if the lines are horizontal or vertical. They're a little bit trickier when you have diagonal lines, which is why I wanted to walk you through so many of those. Okay, so that's a bunch of examples to help you out. All you got to do is finish the rest of it. That shouldn't take very long. And you have a couple days to do this one. So that's going to cover section 11. We're in chapter 11, right? 11. Yep, 11.1 and 11.2. So finish that up and take a picture of it or scan it and turn it in, and you should be good to go on those. The next lesson we're going to talk about rotations, and we're also going to put a couple of these different rigid motions together.